The Big Bang isn't a firework. What you think the Big Bang looks like. Today, almost everyone has heard this sentence. The universe began with a Big Bang. But pause for a moment and picture it. What do you think the Big Bang looked like? If, in your imagination, it's like a gigantic firework, bang matter and energy, exploding outward, scattering into a pre-existing emptiness, then this episode is going to overturn that picture. I'm going to tell you that the firework model, so often simplified in popular science, is not just a little off. It is fundamentally misleading. The kind of wrong that once led people to think the Earth was flat. Because the creation of the universe is not a distant, completed event, something that happened a very long time ago and then ended. What we observe today, galaxies apparently flying apart, does not come from debris, still coasting away from an ancient blast, like shrapnel from a grenade. In a very real sense, the Big Bang is still happening, not as an ongoing explosion, but as the ongoing expansion of space itself, right now, while you're watching this. And here is an even more counterintuitive statement. The universe doesn't expand outward into some external room. There is no outer container. There is no outside for the whole universe to push into. To make this truly clear, we have to be precise about what expansion means. So today, let's settle this properly. What cosmic expansion really is, what it is not, and why the most common mental images are so misleading. This is a long episode, but I promise the payoff is worth it. Let's step back into the deep, strange, and beautiful logic of the cosmos. When the Milky Way was the entire universe. For most of human history, the Milky Way was assumed to be the whole universe. Then, in the 20th century, something happened that nobody expected. Our picture of reality took a sharp turn. That new era began publicly in April 1920, in Washington, D.C., with a famous event hosted by the U.S. National Academy of Sciences, a major debate between two leading astronomers from America's top observatories. One was Heber Curtis, the other was Harlow Shapley. Both were assigned the same theme, the scale of the universe. They were trying to answer two questions that, at the time, nobody truly knew. First, how big is the Milky Way? Second, what are those strange, faint, fuzzy, spiral-shaped patches in the sky, objects then called spiral nebulae, or spiral clouds? Were they just swirls of gas and dust inside our own Milky Way? Or were they island universes, entire galaxies far beyond the Milky Way? Shapley spoke first about the size of the Milky Way. His estimate was somewhat too large, but remarkably close to the truth for the time. Today we know the Milky Way's diameter is on the order of 100,000 light-years. But when it came to the nature of those spiral nebulae, whether they were inside the Milky Way or separate galaxies beyond it, Shapley couldn't give a decisive answer. Curtis, on the other hand, came armed with evidence. He argued that the spiral nebulae were, in fact, galaxies scattered far outside the Milky Way. For example, when the light from these spiral objects was spread out into a spectrum, through a prism, or a spectrograph, the pattern looked similar to the spectra we see from ordinary stars. That strongly suggested these faint spirals were made of stars, not just gas. Curtis also pointed out something else that was deeply puzzling. These spiral nebulae appeared to be moving very fast, often much faster than ordinary stars in the Milky Way. At the time, he didn't know what that meant, but across the Atlantic, a new theory of space, time, and gravity was being built. A theory that would eventually explain motions like these, and in the process completely transform our worldview. A universe filled with galaxies. Today we know the universe is filled with galaxies. Here's a simple way to feel how overwhelming that fact is. Pinch a single grain of sand between your fingertips. Hold it at arm's length against the night sky. In a patch of sky about that size, deep observations reveal thousands, sometimes around 10,000 galaxies. And every galaxy contains billions of stars. So in the observable universe, there are at least hundreds of billions of galaxies, possibly far more, depending on how faint and small a galaxy you count. Now think about the size of just one of them. Consider the Andromeda Galaxy, the nearest large galaxy to the Milky Way, and the most distant object most people can see with the naked eye, under dark skies. In the sky, Andromeda spans an area several times the diameter of the full moon, so in principle, it should be one of the most spectacular sights in the night sky. But it's incredibly faint. With your eyes alone, you mostly see only its bright central region, a small, hazy smudge. Those famous, richly detailed galaxy images you see online, spiral arms, glowing clouds, dust lanes, those are not what your eyes would see. And here's another fact that bends your intuition. A galaxy is so vast that even if it were moving sideways through space at the speed of light, in a human lifetime, it would barely shift its position on the sky. At that scale, galaxies look frozen in place. We can see evidence of past collisions, explosions, and disasters imprinted in their shapes. But we cannot simply watch a whole galaxy drift across the sky in real time and say, "Ah, there it goes." So a century ago, the question was unavoidable. If we can't directly see galaxies moving across the sky, how do we learn how they move at all? 3 guesses about how galaxies move. Now, imagine you know nothing. No modern CGI fly-throughs. No God's eye camera. No simulations. You are a speck of dust, living on one planet, inside one galaxy, in a universe full of distant smudges. From your point of view, those smudges barely shift. Year after year, their positions change by less than the thickness of a hair. You can only form hypotheses. Let's list 3 plausible guesses, each with reasoning that sounds, at first, somewhat convincing. Hypothesis 1. Maybe all galaxies are moving toward us. Because gravity should pull things together. If mass attracts mass, then over time, everything should collapse toward some center. So perhaps galaxies are drifting toward one another, toward the Milky Way destined to collide. Hypothesis 2. Maybe galaxies are not moving at all. Perhaps the universe is in a perfect, balanced equilibrium. After all, if everything had been falling inward forever, shouldn't it have collapsed long ago? Hypothesis 3. Maybe galaxies move randomly. Perhaps they're so far apart that gravity is too weak to organize their motion, so maybe every galaxy just drifts its own way like bees in summer air. Some toward us, some away. Which one would you pick? Here comes the spoiler. Nature chose something stranger than all 3. In 1912, 1913, at Lowell Observatory in Arizona, an astronomer named Vesto Slipher measured the motion of our neighbor, the Andromeda Nebula, using spectroscopy. He found that Andromeda was approaching us at roughly 300 kilometers per second. At first, that seemed to support hypothesis 1. Nearby large galaxies attract each other gravitationally. But then Slipher measured more galaxies. Some were approaching, others were receding. At that stage, hypothesis 3 random motion looked plausible. But as astronomers measured more distant galaxies, something remarkable emerged. Beyond our local neighborhood, the overwhelming majority of galaxies are moving away from us. In fact, aside from a small number of nearby galaxies bound by gravity, almost every galaxy we can measure is receding. That wasn't on our list. So what was going on? Then, in 1929, Edwin Hubble discovered an even stranger pattern. A galaxy's recessional speed is proportional to its distance from us. The farther away a galaxy is, the faster it appears to be receding. This relationship became known as Hubble's law. Now, if you're a human being with a human brain, you almost can't avoid a certain picture. If everything is flying away, faster, at greater distances, then maybe long ago there was a single blast, a cosmic explosion, a bomb. Fast fragments fly farthest, slow fragments stay nearer. It's an easy mental image, and it's the one most people carry around. But that image is deeply misleading. Why the cosmic firework picture breaks? Here is the first problem with the explosion in space picture. If galaxies were simply thrown outward into a pre-existing emptiness, what we see would depend heavily on where we happen to be. Imagine you live on one of those exploding fragments. If you were on the fastest moving fragment, and you looked forward in the direction you're flying, you should see mostly empty space, because you're outrunning everything else. If you looked backward, you should see most of the matter, concentrated behind you. But that is not what we observe. No matter which direction we look, Galaxies are distributed on the largest scales roughly uniformly. Then there's an even more uncomfortable implication. If the universe were a simple explosion with a definite center, then the only way every direction could look roughly the same is if we just happened to be near the center of the blast. Why would our galaxy be special? Why would we be sitting at the center of the universe? That doesn't make sense. And then there is the ancient light, the faint, nearly uniform glow that exists in every direction in the sky, the cosmic microwave background. It is the cooled remnant of the early hot universe, and it reaches us from every direction, not because light turned around, but because, wherever you are in the universe, you are surrounded by a spherical shell of last scattering light that has been traveling ever since the universe became transparent. The uniformity of that ancient radiation is not an awkward detail. It is one of the strongest clues that the shrapnel explosion into space picture is not the right way to think. So if the firework picture is broken, what replaces it? We need an idea powerful enough to explain. Why almost all distant galaxies are receding. Why the recessional speed scales with distance. Why the universe has no special center. Why the sky looks broadly the same in every direction on the largest scales. And the key idea is this. Galaxies are not primarily flying through space like bullets. Instead, the space between galaxies is changing. Space itself is expanding. To understand why that statement is not just poetic but precise, we have to go deeper into what space even means. Absolute space, relational space, and why scale is not as simple as you think. To explain cosmic expansion properly, we have to rewind the story, not to the 1920s, but to a much older argument about the nature of space itself. In the early 18th century, a brilliant and historically influential woman helped ignite a philosophical dispute that would later echo through physics. Her name was Caroline of Ansbach, who would become Queen of Great Britain. She was highly educated, intensely curious, and deeply engaged with the intellectual giants of her time. She recognized that two worldviews were in conflict: Isaac Newton's picture of absolute space and time, and Gottfried Wilhelm Leibniz's relational view. Through exchange of letters, most famously in the Leibniz-Clark correspondence, where Samuel Clarke defended Newton's position, the debate was put into writing. The disagreement can be put simply. Newton insisted that space is an absolute real stage, a fixed background with a God-given scale. A meter is a meter everywhere, always. Leibniz argued something radically different. Space, like time, is not an absolute thing with an independent existence. Space is relational. It is about the relationships among objects, how far, compared to what. To feel how unsettling that is, imagine a photograph. In the photo, there is a car, and nothing else. Could you tell whether the car is full-sized, or a perfectly made miniature model? From the photo alone, you can't. You might say, put a ruler in the photo. But even then, how do you know the ruler isn't also a scaled miniature? You only ever know size by comparing one thing with another. Now push the question further. You and I, everything we can touch, every ruler, every atom, what scale are we built on? Are we normal-sized humans? Or are we tiny people living in a dollhouse universe? If there is nothing outside the universe to compare against, big and small begin to lose their absolute meaning. And then comes the deepest question. Is the scale of the universe the same everywhere? Is it the same at all times? Could the length of a meter vary in different places, or evolve over cosmic history? To Newton, such questions were nearly meaningless, because absolute space defined an absolute scale. But Leibniz's instincts pointed toward a future in which scale could be tied to physical relationships not handed down from outside. Leibniz died soon after, and Newton's framework dominated for centuries. But the idea that space and time might not be rigid, that they might stretch, compress, and respond, did not die. It re-emerged in mathematics, most powerfully in the work of Bernhard Riemann. Riemann dared to question the old assumption that the length of a line is independent of where that line is. He developed the foundations of what we now call Riemannian geometry, a way of describing spaces in which distances depend on position spaces that can be curved, warped, and dynamic. That mathematical language would later become essential for the next leap. Light forces the universe to abandon common sense. By the late 19th century and early 20th, A chain of discoveries forced physicists into a shocking conclusion. The size of things, what counts as a length, and the flow of time, could not remain universal and absolute. The most explosive clue came from the most ordinary phenomenon imaginable: light. Experiments showed that the speed of light in vacuum appears the same for all observers, regardless of how fast the observer is moving. If you tell someone that casually, they might shrug. But if you truly sit with it, it becomes unbearable. If you chase a beam of light at 99.999% of light speed, the beam still moves away from you at light speed, as if you were standing still. How can that be? This paradox was resolved through ideas developed by Hendrik Lorentz and brought to their sharpest form in 1905 by Albert Einstein: special relativity. The price of saving the constancy of light speed was enormous. You must give up the Newtonian hope that there is one universal clock and one universal ruler. Different observers, moving relative to one another, do not agree on lengths and times in the same way. Time dilates. Length contracts. These are not errors of measurement. They are how reality works. And once you accept that, a domino chain begins. If time and length depend on motion, what about gravity? Newton's gravity assumes an absolute stage beneath it all. Einstein realized that stage could no longer be trusted, so he set out to rebuild gravity itself. Einstein's gravity, and the fact that space can change. Over roughly 10 years, Einstein searched for a theory that could respect conservation laws, be consistent with special relativity, and describe gravity not as a mysterious force at a distance, but as something woven into space and time. In 1915, he finished general relativity. Conceptually, the core is simple. Mass and energy affect the geometry of space-time. Space-time tells matter how to move. Matter tells space-time how to curve. In Newton's world, mass, time, and length are independent quantities. In Einstein's world, they are deeply connected. Mass changes the behavior of clocks and rulers near it, not because objects choose to change, but because the geometry they live in is different. The equations were so advanced that at the time almost no one could work with them. And yet, the first major test came quickly, not from Einstein himself, but from someone in an almost unbelievable situation. Carl Schwarzschild, serving on the front lines during World War I, found the first exact solution to Einstein's equations for a simple case: a spherical mass. He wrote to Einstein with the solution and applied it to real problems. One famous success came from Mercury. Newtonian gravity explained the orbits of the planets extremely well, but Mercury's orbit showed a tiny discrepancy. Its perihelion, the point of closest approach to the Sun, precessed slightly more than Newton's theory predicted. Schwarzschild's solution and Einstein's theory accounted for that missing precession with stunning precision. It was an early sign that this abstract geometry was more than mathematics. It described the real world. Schwarzschild's work also laid foundations for one of nature's strangest possibilities: black holes. And it helped solidify an idea that matters for our story today. Space-time is not a fixed background. It can be warped. It can change. Even gravitational waves, ripples in space-time, can pass through you right now, stretching and squeezing lengths by unimaginably tiny amounts. You don't feel it because the effect is minuscule. But the fact that such stretching and squeezing is physically real tells us something profound. Space is not just emptiness. It has structure, and that structure can evolve. Now we are ready for the critical step. What happens when you apply Einstein's gravity not to Mercury, not to Earth, but to the universe as a whole? Expansion is not galaxies flying through space. In 1916, and the years that followed, Einstein and other physicists asked a bold question. Suppose we idealize the universe as homogeneous and isotropic, meaning, averaged over enormous scales, matter is distributed roughly uniformly. This is not claiming galaxies are evenly spaced like a crystal. It's saying that if you take a gigantic volume, hundreds of millions of light-years across, the clumpiness smooths out statistically, the way air looks uniform if you don't zoom in to see the molecules. Now apply general relativity to such a universe. What happens to the geometry of space over time? The answer is startling. Einstein's equations do not naturally prefer a perfectly static universe. They generically imply that the scale of the universe should change with time. In other words, a universe filled with matter and energy is not forced to remain the same size. It can expand or contract. But here is where language traps us. When we say the universe expands, many people immediately picture a balloon swelling into surrounding air. That image is not what the equations mean. To build intuition, imagine this. Picture a large cube of space, a representative chunk of the universe, filled with evenly distributed matter. Now put a ruler inside the picture. Call it a cosmic ruler. Let's say the cube is initially 1 cosmic ruler tall. As time passes, the mathematics of an expanding universe says that the scale factor changes distances between widely separated, unbound objects grow. There are 2 equivalent ways to describe that change. You can say the cube's height increases in terms of the ruler, or you can flip the picture and say the ruler shrinks relative to the cube. In everyday life, those statements don't feel equivalent because we assume rulers are absolute. But cosmology is about relationships of scale across the whole of space. The key point is not which metaphor you choose. The key point is this. The recession of galaxies is not best understood as galaxies being hurled through space by an explosion. Instead, it is space itself, the distances defined by the geometry of the universe changing over time. Now imagine your galaxy sits in one corner of the cube. You look toward a very distant galaxy near the opposite corner. You will see it receding. And the farther away it is, the faster that recession appears because more changing space lies between you. This is the heart of the matter. Galaxies are not primarily running away through space. The distance between galaxies grows because the space between them evolves. And this immediately explains Hubble's law. The farther a galaxy is, the more expanding space lies between you and it, so the larger its recessional speed. It also explains why we do not see noticeable expansion inside the solar system or inside the Milky Way. Local systems are held together by gravity and other forces, strongly enough to resist cosmic expansion. Cosmic expansion becomes dominant only across truly vast, intergalactic distances, scales where galaxies are not bound into a single structure. The change per year is tiny, far smaller than anything you could notice on human scales. But across billions of light years, tiny effects accumulate into enormous separations. This also resolves another famous point of confusion. Very distant galaxies can have recessional speeds greater than the speed of light, not because they are violating relativity by moving through space faster than light, but because the metric that defines distance across space is changing. Light speed limits are limits on motion through local space. The expansion of space itself is a different kind of phenomenon, and it implies something else. There are regions of the universe so distant that their light will never reach us, because the space between us and them expands too quickly. We live inside a finite bubble, called the observable universe, not because the whole universe must be finite, but because light has had only a finite time to travel, and the universe's expansion shapes what can reach us. There is no outside, and no explosion center. Now rethink the question people always ask. If the universe is expanding, what is it expanding into? The answer is, it is not expanding into anything. Cosmic expansion is not the universe swelling into an external emptiness, because external emptiness would itself be part of a larger space, and the universe, by definition, is the totality of spacetime. There is no guaranteed outside in the physics. That's why popular analogies can mislead. The raisin bread analogy, raisins separating as dough rises, can help illustrate why every galaxy sees other galaxies receding. The balloon analogy, dots separating on an inflating surface, can help illustrate why there is no special center on the surface. But both analogies can quietly smuggle in the wrong idea, that expansion happens into some larger container with a fixed external scale. In modern cosmology, expansion is ultimately about the changing scale factor, a change in how distances are defined across the fabric of space. If you want an intuition that avoids the expanding into trap, you can flip the metaphor. Instead of imagining space getting bigger out there, imagine that, over cosmic time, the scale of everything unbound by local forces is rescaled, so that what we call a meter would represent a different fraction of the cosmos than it did long ago. Again, this is not saying your body literally shrinks in your own frame in any everyday sense. It's saying that cosmic expansion is not best pictured as debris, moving through a static background. It is the background geometry itself evolving. So when someone asks, where did the Big Bang happen? The most honest answer is, it happened everywhere, not at a single point in space, but as a condition of the early universe. A hot, dense state from which space-time expanded. And when someone asks, is the Big Bang still happening? A careful answer is, the early hot, dense phase is in the past. But the cosmic expansion that followed from that beginning is still ongoing, everywhere including here, right now. Einstein's hesitation and the cosmological constant. Here's a twist in the human story. Einstein himself struggled to accept what his own equations implied. At first, he believed the universe must be static. Space looked stable. Stars looked almost motionless. Surely the cosmos wasn't changing on the largest scale. So he added an extra term to his equations, the cosmological constant. Its purpose, in his mind, was to counteract gravity and hold the universe in a static balance. Years later, as evidence for expansion became overwhelming, Einstein reportedly regretted that move, calling it his greatest mistake. History is complicated, and the exact wording is debated, but the central point remains. He introduced the cosmological constant to allow a static universe, then later accepted expansion. And in one of the great ironies of science, the cosmological constant didn't disappear. In modern cosmology, a term mathematically equivalent to a cosmological constant can describe what we now call dark energy, a component associated with the observed accelerated expansion of the universe. This is a reminder of what scientific revolutions are really like. From the outside, people imagine sudden flips in belief, but scientists are, by nature, conservative about new claims. Every radical idea demands extraordinary evidence. Even Einstein doubted his prediction. Even Hubble's early measurements had uncertainties. It took time for the new picture to become unavoidable. The Big Bang as a conclusion, not a cartoon. When we run the expanding universe equations backward, something dramatic happens. The scale factor shrinks toward an early state where density and temperature become extremely high. In idealized mathematics, that extrapolation can lead to infinities, a breakdown called a singularity, where the theory no longer describes physical reality. That is not a sign that the universe came from nothing in a simple sense. It is a sign that our classical description, general relativity, without quantum gravity hits its limit. But here is what remains solid. The Big Bang is not merely a metaphor. It is not a vague guess. It is not just a story. It is a conclusion supported by multiple lines of evidence, especially cosmic expansion, the cosmic microwave background, and the abundances of light elements formed in the early universe. And yet, for the sake of public understanding, a mathematically precise picture was gradually simplified into a cartoon. A bomb in space, a firework in emptiness, a blast with a center. That cartoon is seductive, but it triggers the exact questions that then confuse people. Exploded into what? What's outside the universe? Where is the center? Those questions are not stupid. They are what happens when you apply ordinary explosion intuition to something that is not an explosion into an external room. So here are the two takeaways I want you to leave with. First, the explosion is a very inaccurate metaphor. The universe did not explode outward into a surrounding void. There is no required outside and no required center. Second, the growth of distance between faraway galaxies is tied to the ongoing evolution of space itself. The change is tiny locally, but it accumulates across immense distances into the grand cosmic pattern we observe. So grand that the farthest galaxies can recede from us faster than light without violating relativity, because the phenomenon is not motion through space in the everyday sense. Now, for a moment, set aside the debates, the competing metaphors, the arguments about words. Just walk with me, briefly, inside Einstein's strange, elegant world, a universe where space, time, and matter are not separate ingredients, but a single intertwined system. A universe where the cosmos is not merely a stage, but part of the plot. A universe that, in a sense, is always being made continuously unfolding its geometry. The Big Bang didn't happen somewhere else. It happened here, where you are sitting, because every here was once compressed into the early universe's tiny, dense state. The atoms in your body, and the atoms in distant galaxies, share a common origin. They were once part of the same hot, connected reality. And now, through the long, silent evolution of space-time, they are separated, not by an outward blast into darkness, but by the deep, ongoing transformation of space itself. We live inside a creation bubble. The universe is never idle. It is always becoming. And that is the strange, beautiful picture of reality we've earned through centuries of thought, doubt, and discovery.